Okay, let's go through the projectile examples. The first one, we've got somebody running off the top of a building and falling into a pool. So I always start by drawing a picture. Okay, we're given the height of the building is 30 meters. And the person is running across the building. When they leave the building, they're going to be a projectile. So we're going to take that parabolic path, and then we're told the pool is 5 meters from the building. Alright, so the question is, what is this velocity when they leave the building? So because the top of the building is horizontal, that velocity leaving the building is all going to be horizontal. I always start with what I'm looking for. So in this case, I'm looking for the velocity in the x direction. Now remember what we talked about in class, the velocity in the x direction is constant. So I don't call that initial, I don't call it final, I just call it Vx. The whole flight of this person, the velocity in the x direction is going to be the same. We know the displacement in the x direction is 5 meters. So we're missing a piece of information here to solve for the velocity, and that's going to be time. We're going to get time then from the y direction. The time it takes the person to fall 30 meters is going to be the same time it takes the person to go across 5 meters. The initial velocity in the y direction is 0 because when they leave the building, they're not moving up and down. We know the acceleration, negative 10 meters per second squared, acceleration due to gravity. Our displacement, I'll call that delta y since we're looking in the y direction, is going to be negative 30 meters because we went down 30 meters, and then we can solve this for time. So looking at the variables we have, we pick the kinematic equation that matches that, and that's going to be the delta x equals initial velocity times time plus 1/2 acceleration time squared. So we've got negative 30 equals 0 plus 1/2 negative 10 time squared. We solve that for time, and we should get 2.45 seconds. So then we can use that in the x direction. Now, the only equation we ever need in the x direction is v equals delta x over t. Because the velocity is constant in the x direction, I just always use this one. I don't need to worry about the 4 big equations. They all have acceleration in it. We don't have acceleration. So the velocity in the x direction equals delta x, which is 5, over time, which is 2.45. Solving that, we get a velocity in the x direction of 2.04 meters per second. So that's part A. Part B, determine the person's final velocity components and the final resultant velocity. Okay, well, we just talked about the velocity in the x direction is always constant, so the final velocity in the x will be 2.04 meters per second, always the instant before it hits. If we're talking after the person hits the water, then other physics is going on there, and we can't call that 2.04 anymore. In the y direction, okay, I'm going to use the same information right here, but now we're going to look for the final velocity in the y direction. Okay, I'll label this y. Alright, so given that information, we can use v squared equals v naught squared plus 2a delta x, or delta y in this case. We're looking for the final velocity. Initial velocity is 0, 2 times negative 10 times negative 30. So we get our final velocity in the y direction of 24.5 meters per second down. Okay, so that's our y, and there's our x. Okay, to get the total velocity, alright, I'm going to redraw these vectors. Okay, so we have 2.04 in the x, and then a y, I've got 24.5 meters per second. So the resultant, again, always start at the start, end at the end, so that's going to be the final velocity. Velocity is a vector, so we use Pythagorean theorem to get this, so the velocity will be square root of 2.04 squared plus 24.5 squared, which gives us about 24.6 meters per second. Now, that's not our final answer because remember, velocity is a vector. We do need a direction with this. So I'm going to label that angle theta. We can use trig to get that. So theta, you say the inverse tangent of 24.5 over 2.04. You solve that for theta and you get 85.2 degrees. Now, I wouldn't just leave it like that. We can be more descriptive with this. So we can say 24.6 meters per second at 85.2 degrees below horizontal. And that clearly shows the direction. So there's our entire answer for question number 1.